Everybody, I'm going to talk about enolates in this video. So this is going to be kind of our introduction to enolates. It's going to go over how we form enolates, and we're going to really kind of dive into the different types of enolates that you can form and what bases are best to use. So just as a reminder, we have actually seen enolates before. We've also seen enols before. We're looking at very similar things. The important thing to keep in mind is that all of this is acid-base chemistry. So we're looking for any kind of most acidic proton. So we want to remember that our first semester mantra of protons on atoms next to pi bonds is kind of our key pattern that we're looking for here. And that's specifically what makes an enolate. So we're looking at, this H that's on a carbon that's next to that carbonyl. You can make enolates from a bunch of different types of carbonyls. I'm going to show you with ketones today, but you can also do this with esters, aldehydes, anything that has this. This is called an alpha position. So anything that has that alpha position of something with protons next to a carbonyl is going to be that alpha position. So if we're using a base, that base is going to come and grab that H. We're going to push electrons up onto the carbon. And then we have our enolate, okay? And we do want to keep in mind that the reason that that's so acidic is because we do have this resonance structure where we are able to delocalize that negative charge onto the oxygen, which is a much more electronegative atom. So when we're looking at this, we're really looking at, this is kind of going to be the reactive form. Okay, so if we're trying to draw a reaction, oftentimes this one is a lot easier to kind of follow along because we're looking at this nucleophilic carbon right here is kind of the thing that we're interested in. But then we also need to keep in mind that this one is definitely our major resonance contributor. So that's definitely kind of the major form of resonance, but this is the one that we're specifically interested in for reactions. And again, these are our enolates. Okay, we also know that we can make enols with acid. So if we want to use an acid here, we can first protonate that oxygen of our carbonyl. And then we can go ahead and deprotonate the carbon. And then that has given us our enol. Okay, so I will say the enolates, these are a lot more common. But you can see enols used. So if you see like an acid version, you can do similar enolate chemistry with the protonated form of the enol. Okay, so we're going to focus mostly on the base versions, but I do just want you to know that this does exist. Okay, so let's check out some acids and bases here. So let's take a look at cyclohexanone. And to get a good understanding of enolates, it really helps to think about pKa's. So if I take sodium ethoxide and I've got cyclohexanone over here, the pKa of cyclohexanone is 16.7. So if I do my acid-base reaction here, okay, then I get my enolate and I get ethanol. Okay, so ethanol has a pKa of about 16. Okay, so if we look at that, we have a very slight preference for the reactants in this acid-base reaction. So there's a small difference between the pKa's. So we've got a slight preference for the reactants because that's the larger pKa side. So if we're looking at this, if they were completely even, we'd have basically 50-50. So essentially what we have is we kind of have 60% of our ketone present versus about 40%-ish of our enolate. Okay, so that's a situation that, you know, I am kind of making up those numbers a little bit, but I just want to show you, like, we're kind of a little bit more on the reactant side, but we're still forming some enolate, but we have both present in the solution at the same time. And I just completely missed my numbers here. Okay, so that's an ish estimate. But we want to keep in mind both the ketone and enolate are present in the reaction at the same time. Okay, so we want to keep that in mind when we're thinking about this, because this in this form is an electrophile. We've got that ketone as our electrophile. And then over here, we have made a nucleophile. Okay, so I just want us to keep in mind that we need to make sure that we have that clear, that when we're in that, you know, protonated form, it's certainly an electrophile right here. But then as soon as we deprotonate it, now we've turned it into a nucleophile for any reactions. So if we have both of these things in the reaction at the same time, they can actually react together. All right, so let's look at another base. So let's take the same ketone here. So we're going to look at cyclohexanone again. And we're going to look at LDA this time. Okay, so we're going to use the lone pair of the nitrogen, go deprotonate that ketone, form our enolate, form our conjugate acid. So pKa over here again is about 16.7. And then the pKa for the diisopropylamine is 36. Okay, we have a huge difference in pKa here. So that really, really large pKa difference, products are heavily favored. Okay, so I really should change this arrow to be like this, noting that this is now an irreversible step. Okay, whereas up here, this equilibrium arrow is definitely correct because we're not going to have 100% of either side. We're going to be kind of floating in between them at some dynamic equilibrium. So in this one, though, since our pKa differences are huge, we're going 100% to product. So we're going completely to the product side. So we're going to have only enolate present. And no ketone. Okay, so we're getting full conversion to that enolate, and there is no equilibrium here. Okay, so let's look at another way that we can get that big pKa difference, but without using something as aggressive as LDA. Let's just label this as LDA. All right, so let's take a look at a different type of carbonyl environment. Okay, so let's look at this guy. So in this case, we actually have 2 alpha positions right? We've got one in between the two carbonyls, and then we've got one to the left of the carbonyl. So if we were going to do our, acid base analysis in terms of finding the most acidic proton, we should immediately jump to this guy, just because we can delocalize up onto both of those oxygens if we're in between both of them. Okay, so we're going to have this guy. We're going to add sodium ethoxide here. So we're going to have that sodium ethoxide is going to go grab that H. And it's important to think about, whenever you've got an ester here, just making sure that this matches this, just because that's going to make sure that if we do any kind of basic transesterifications, we're not going to see that happen, and we're just going to get the same ester out again. So if this comes in and goes up and then goes down and then kicks that off, we still end up with the same ester. So we don't really care if that's happening. So it is helpful to make sure that your bases are matching when you have an ester present. Okay, so we've got that acid-base reaction. Okay, so we've got our enolate here. Let's just draw out the resonance structures to show that this is really, really a stabilized one. Okay, so we can go up onto that oxygen. We can come down, go over to the other one. Okay, so we've got that charge delocalized over 2 oxygens and 1 carbon. So if we look at the pKa here, this pKa is about 9. And then, again, we've got ethanol as our conjugate acid, and that pKa, as we've seen, is 16. Okay, so again, we have a situation where we've got a pretty big difference in pKa. It's not nearly as large as with LDA, but we still have that large pKa difference. Okay, so we still have products heavily favored. And so we're going to have maybe like a tiny little bit of reactant, but it's going to be pretty negligible. Okay, so that's kind of what we want to think about. There's different situations where you want different things. So, do you want to have all enolate formations so then you can just kind of throw in whatever electrophile you want? Or do you want to have some sort of equilibrium process present so that you can have both the ketone and the enolate? It just depends on what you want. So you have to make sure that you kind of have a good understanding of what's going on with the differences in our acidities between our acid and our base. So you can kind of determine how much enolate are you forming compared to how much carbonyl do you have remaining. So the last thing we need to talk about with enolates is we have kinetic and thermodynamic enolates. Okay, so far I've only talked about enolates where there's really only one or symmetrical options between alpha protons. But let's look at a situation where we have multiple options that are different. So if we just take a look at 2-butanone, so we've got 2 alpha positions here. So we've got one alpha, the other alpha. One has 3 H's on it, and one has 2. So we definitely have one side that's kind of more hindered and less hindered. So when we're thinking about kinetic, again, we're always looking at speed. So it's about which one is the easiest to get to. That side is going to be the easiest to get to. But this side is actually going to be our thermodynamic product, and I'll show you why. So let's look at LDA first. So again, remember the structure of LDA. We've used it in the past for E2 reactions as a bulky base. Okay, and that bulkiness comes from these two isopropyl groups that are chilling by it. So when we have this nitrogen lone pair go grab an H, we're really saying, actually, let me do it in. We really need to be thinking about the fact that these big isopropyl groups are going to get in the way of us kind of accessing more hindered alpha protons. So we're going to get to this enolate, okay, which is in resonance with the other form. And for thermodynamic, we're really going to look at this alkene. So let's look at the other one, and I'll show you why that is. Alrighty, so if we take the other side, some sort of like OR minus, so that could be OH minus, it could be OME, OET, any of those kind of small oxygen bases. When we're looking at that, that's a much smaller situation, so we can fit into those tighter spaces a lot easier. Oops, what am I doing? Okay, so I can end up with this enolate, which is then in resonance with this one. And this is the important part. So right here, this alkene that we've made is more substituted than the other side. Okay, it's not a true alkene, but we're still looking at kind of the same ideas here. So this more substituted alkene makes it more stable. Okay, so this is our thermodynamic product. This one over here is the fastest formed because it's the least hindered, which makes it the most accessible side. This is the kinetic enolate. Okay, and the thing to keep in mind here is that this is always the fastest to form, even in this case. The key here is that this reaction, because of that difference in pKa that we've seen before, where there's definitely a big equilibrium going on this side, the fact that we can go back and forth is what allows us to kind of, you know, get to this enolate first, and then it can go grab an H and equilibrate back to this. And eventually it's just kind of going to jump back and forth until it eventually filters into that lower energy thermodynamic enolate and kind of gets stuck there when it gets there. So that's kind of what we're looking at for kinetic and thermodynamic. We're looking at more substituted, less substituted. It's not going to come up a ton, but it is important for us to kind of think about, you know, what's the fastest enolate to form versus what's going to be the most stable enolate to form. Alrighty, so as always, let me know if you have any questions, and if you want to binge these, go ahead and follow on to the next one that's going to talk about what we do with enolates.